say, quantum harmonic oscillator. So we first gonna check what's just the bosonic case. What do we mean by that? So suppose you have the algebra, and it's generated by two elements, A and A star, and it's subject to the following relation that you have A star, and then the commutator. So this is just A star minus A star A is equal to 1, and A star and A, they commute. So this is the only restriction we want to put on this algebra. So in physics we would say, okay, A star, or we will say later, that A star will be a creation operator and A will be an annihilation operator, okay? So A star is supposed to create a particle, a boson, and A is supposed to annihilate it, okay? So what we then want to do, like this quantization business is kind of about representations, right? Like we heard the slogan that particles or quantum particles are just some elements of some representation space. So what we want to do is we want to consider the lowest weight representation of A. What does this mean? This means we want to consider a state, let me say here, 0, which is supposed to be the vacuum. So this is purely algebraic, okay? Assume there exists such a thing where A can act on, right? Like A and A star act on this guy. This is the element of the vector space of our representation of A, such that A of 0 is just 0, okay? Then we can define the actual Hilbert space where now the algebra actually acts on. We build it purely from this state. So let me call this H bosonic, and these are all n's where, let me just write how they look like, where we act n times basically with the creation operator on the state. This is just by definition, and n is probably an n somehow. And so now we can just act on it, and then let's define kind of natural operators. Yes, sorry.
Isn't it n factorial here?
Sorry?
Isn't it n factorial?
It might be, yes. Thank you. It might be. Yeah, we will not do anything with that. I just want to say this is a normalization thing, but like it's good to have good normalization. So, so let's see kind of how we act on it as well. Basically, we act with a creation of like with A star just by augmenting n, right? And we act with A by more or less annihilating one of them. Okay, and how would we do this? Well, for example, one usually defines this number operator and B, so it's called the number operator.
It's just it's a vector space. You have other.
Which is just given by A star A. And this is a small exercise. You can show that it's diagonal in the spaces. Okay, so I'll just give you certain operators and show you how they act on this representation. Moreover, you can show, and this is another small exercise, but I don't want to give it state it as an exercise, but you can show the following commutation relations. This is just A star, and then the number operator on A is just minus A, right? And then I already said it's diagonal in the spaces. So yeah, so essentially this relation, right, means that A star of n has kind of eigenvalue n plus 1 under nb. Does this make sense? Roughly? You've seen this maybe? So it's like this Fock representation. So what I'm trying to say, if you look at this, right? then what is this? Then you have NB A star, and let's put the commutator here, but then you have to put an A star NB, right? On N. So this we said is A star, right? So this gives you N, this gives you A star. So essentially you have N plus 1 times A star of N, which would mean that A star of N should be N plus 1. Okay? And similarly, if you just apply A on N using this commutation relation in the exact same manner, you can show that you go lower here. Okay? You go N minus 1. So, since we're talking about physics, we should talk about the energy. The energy, let's say I'll just give it to you as a definition, but if you go through the process of quantizing the simple harmonic oscillator, you would find it in this way if you do a canonical quantization. It has this information parameter h bar, which indicates that we're in the quantum world. It has some kind of frequency, let me call it omega b, and then usually you have some kind of offset, but it's basically just measuring the number of particles, of bosonic particles you have. Okay, so essentially what it says is that you have a ground state energy which is 1/2 h bar omega bars, like one quantum, yeah? And then NB, like each n, right, each particle, let's say, carries a quantum, and then NB just measures how many there are. So this is kind of this energy idea. Good, so since NB is diagonal, the energy is also diagonal, right? So this is just the energy of the state N. So this is energy of state N. Good. Okay, so let's see, sorry, let me just put, let's see what happens for fermions. Okay, so these are kind of bosons. And let's see how we would do the same for the fermionic quantum harmonic oscillator. So again, you can probably think up a physical model for it, but you could also just say that this, let's say, is the representation theory of the algebra lambda, which is the algebra generated by two elements, C and C star, but now they have slightly different restrictions, right? These generators, so they're subject to, and now there's this anti-commutator bracket, which just basically puts a plus between them. But this is 1, and actually you will say that C squared is equal to C star squared is equal to 0. Okay? So the oddities start here. This is again an odd property. Okay? This thus has a very important consequence, and let's explore it. Well, we actually do the same stuff as before. So now we want to see the lowest weight representation. So we have a vacuum 0 defined by C being annihilated, and then we will call C star of 0. This would be the natural next state. Let's call it 1. Okay, and think of it as being like the state is occupied by one fermion. So now what happens is, by these strange relation is, what would be the natural 2? Well, this would be C star acting on 1, but this would be C squared on the vacuum, but this is 0 because C squared is 0, or C star squared is 0. And this is kind of the odd part, because it basically says our Hilbert space, right, for these fermions, they're just, it's finite dimensional, right? So it has a state 0 and then it has a state 1. And basically it says fermions don't like each other that much. They don't want to occupy the same state. Yeah, odd fellows, as I said. So as I said, I want to just do the same thing. We define this number operator C star C, and then it just counts, right? So n of, let's say, how do I want to do that? M is M. How do I want to do that? Yeah, for M in 0 and 1, right? And then we just define in similar fashion, kind of, we think that each fermion has a quantum of energy, and then we just count all of these. But then here we have a -1/2. Okay, so there are two minus signs happening. So one is in the commutation relation, where we had bosonic, we had the usual defined with a minus, and now we have defined it with a plus. And then in the energy, which is here, we have a plus here and we have a minus here. Okay. So here's a remark, just to see like, okay, maybe this is not so nice, right? Like probably this is just some abstract nonsense, and we should probably give an example of more stuff we understand better. So there's a realization, and in fact there's a matrix realization. And what's this matrix realization? So you take C to be, which one I want, 0, 1, 0, 0, and you take C star to be the matrix 0, 0, 1, 0, and then your fermionic Hilbert space will be just basically acting by fundamental representation on R2. And H is what? It's H bar omega, I think, over 2, 1, 0, 0. -1. And you see that C squared, this is an important element, so this does square to 0. So these things exist, right? So, and they're not too scary actually. And actually, because they square to 0, they lead actually to something very nice, namely the finite dimensionality of the Hilbert space. So, okay, so maybe they're actually our friends. Let's see. Okay. So, finally, let's put it all together, right? So we have this boson, quantum harmonic oscillator. So this is of course not a Q for headquarters, but probably harmonic oscillator. Okay. So let's put it together and see if we can build this thing. So what would we do if we would put both together? Very naively, we can take just the algebra W, which would be A tensor lambda, okay? And this is generated by A star and C star, and then subject to same, or to the commutation relations as before. Meaning that C squares to 0, C star squares to 0, A and B commute to 1, and C and C star, they make this funny commutation here to 1, okay? Sometimes you say anti-commute to 1. Then, again, let's start the lowest weight representation. We're actually going to study a lowest weight representation for all of it. So we will have the state 0, the vacuum, such that it's annihilated by C and by A. So nothing is occupying it at all. I just want to say one thing because I will mess it up. I will kind of forget about this tensor product and kind of have it in my head somewhere. And this kind of what I want to do is they act on different spaces, these A's and C's. Okay? So you, I want to be really changing them around. Okay? A and C. So otherwise you could just say they're generated by these guys, subject to the commutation relations as before, while A and C always commute, and A and C star commute, etc. So, yeah, basically now what would be the Hilbert space? As I said, right, since they all commute, the Hilbert space will essentially be like the Hilbert space for each other, but you know, meshed together, and the sum. So these states will be just states which can be occupied by any number of bosons, and then either have a fermion or not, right? So this NB is an N, and then this NF is in 0 or 1. Good. So now, what happens is, this is not special, but now the special thing happens. Ah, sorry, I should give you the Hamiltonian first. So the Hamiltonian of the full system is then just a Hamiltonian, like the sum of the Hamiltonians of both systems. So this has this quanta for the bosons, and these quantas for the fermions. And now you can already guess what happens. Is like, oh, we have a plus 1/2 here and a minus 1/2 here. So let's just explore what's going to happen if those terms would actually cancel. Okay, so let's assume that these frequencies are just the same. Okay, so assume omega f is omega b. Then h and then just put this to some frequency omega, just looks like NB plus NF. And why is this actually great? Observations. The first one is the energy now depends kind of on how many bosons we have, how many fermions we have, right? Well, this is h bar omega of, well, NB plus NF, but let's say that this is a positive quantity, okay? Then this is always greater or equal to 0. So we have a positive energy spectrum, which is nice. The second one, suppose that the energy of a given state is non-zero, then these states come in pairs. Why is that? Well, the energy, if you look at it from here, of the state where I have no fermion but plus 1 boson is actually the same, right? As if I have 1 fermion and just n bosons. Well, that is kind of cool, right? Because I mean, there's this would be like a purely bosonic thing. So there's no kind of C star involved in here. While this one, this state, right? This is fermionic. So there is a C star involved. Okay, so kind of these energies, if they're not zero, they come in pairs for usual bosonic one and something which is more like a fermionic one. And now I said that supersymmetry is supposed to be a symmetry between fermions and bosons, and indeed you can show that there is actually a map between these states which then point to the other, which basically means it adds a fermion or takes it away. Yeah. Yes. Okay, so let's look at this. I should not have. Okay. Let's look at this strange symmetry. So the third observation is kind of, there exists a map, let's say, between these state stays. Okay? And how does it look like? Well, this map is Q, h bar omega, let's say, with a square root, taking square. And let's say going in the other direction, this would be h bar omega, and then you would have C and A do. Okay? And since I talked a lot now, let's do a small exercise. No, let me not. Yeah, let's do it. The exercise is the following. Show. First, q squares to 0. Second, q star is actually Hamiltonian. And third, deduce that basically h and q commute, which means q is a symmetry. And then, okay, I'll give you like a couple of minutes to just see how far you get.
Kind of uniqueness statement, like those Q's, Q and Q star that you wrote down are the unique Q's that satisfy those properties?
I'm pretty sure there is in this case, and also in general, yes. There's usually, at least in these physical systems, there is a uniqueness. Well, sorry. Sorry, I shouldn't say. There is an upper bound of how many Q's you can have. Sorry, it's not unique, but there's an upper bound. But this is then more complicated from...
Those rules they kind of generate algebra.
Yeah, exactly. And then, like, yeah, usually they come up in like super popular algebras and they don't and things like that. So there's restrictions due to that. But, yeah.
Well, you said that W is generated by A star, C star, subject to the relations before, but you have not said how A and C interact.
No, that's what I meant. They commute. Like A and C commute. Like bosons and fermions, they don't care about each other. Fermions are very self-centered. They care if I occupy the state, me, myself, and I, and then it's it. Okay. So yeah, but they commute. So that's why I don't write any kind of tensor symbols. So yeah, okay, let's probably look at it. I did the calculations yesterday and then forgot to put them in my notes. You should never calculate, that's a piece of advice, never calculate on the board. Let me break my advice and try to do it. So the first one, q squared, well, by this argument I just said, since A and C commute, it's proportional to C squared, so this is 0. All right. So, yeah, okay. By definition of this bracket, I'm sorry, this is q star plus q star q, right? So what is this? This is h bar omega, and now you have c star a c a star plus c a star c star a. Okay. So this is h bar omega. Okay, and what we kind of want to show is that it's h. So let me just swap these guys, and then we have c star c is already there, which is good. So we can write this as nf aa star, and then plus, and here we already have kind of the nb, so we have here be CC star and B, right? But CC star by the commutation relations of C and C star is 1 minus Q star C, and AA star by commutation relations is 1 plus NB. Okay, so then we have NF, NB, and then NF, NB, so they cancel because they come with a sign, and we just left with the 1, so this is NB plus NF, which is H. Yeah. And then the third part is HQ is essentially, as we said, QQ star plus Q star Q of Q, right? And then you just write it out, I think. So this is the first part, QQ Q star plus Q star QQ minus Q Q star Q. So Q squares to 0. This is not here, this is not here, and here we just have the same factors. So this is 0. Cool. Okay. Now, what we say, since this is such a nice thing, is that Q and Q star, they generate a supersymmetry, which is a symmetry between bosons and fermions. And yeah, so the important part is that our system is kind of invariant, right? It's the symmetry. It's invariant under this strange kind of symmetry, which mixes kind of bosons and fermions. However, they had these huge applications, which we see here somehow, that the energy spectrum is bigger than 0. And if the energy is not 0, then they all come in pairs. And then they all come in pairs with opposite sign, right? So, I don't know if I want to write this already, but so you could. And let's try to do this. So what you can try to come up with is some kind of partition function which is characterizing the system, okay? So it's supposed to be kind of the sum, so let Z be defined, and now I should be careful, as the sum of all states in our Hilbert space by, and now I will introduce something which is minus 1 to the power of f. I'll say in a second what it is, what's supposed to be. Let's say the energy, so usually, I don't know, you have some beta, which is some kind of inverse temperature. We're doing now physics, huh? This is great. The Hamiltonian. And you should take the trace of all this. Okay, so if you have, of course, in statistical physics and things, so this is kind of the partition function at finite temperature, which is supposed to kind of tell you how your, let's say, states are distributed over the energy spectrum. Now, since we have this odd symmetry, we kind of sneaked in this little guy here, and this is just measuring kind of the number of fermions in your state. And then it gives a minus or a plus, okay? So this guy is minus 1 if there exists a fermion, and plus 1 if not, okay? And, well, if you do this in the spaces, right, so you sum over these this NBs and NFs, right? And then, yeah, okay, let me do it. NB and F, so this is how usually you kind of write the stuff. Then in the spaces, we have that the energy is, the Hamiltonian is diagonal, so this will be just this guy, and then you have here NB and NF. Okay, so now let's do actually this calculation. So we first, NF can just take two values, so let's sum this guy first, okay? So there's either a 0 or 1 here or here. So this counting of fermions, it's independent of like all kind of energies and stuff. Anyways, this is scalar. So it will have 0, like it will have a plus sign if there's no dot here, and it has a minus sign if there is 1, right? So there's like some kind of NV0, and then let me just take out this energy thing. No, I should not take out this energy thing. NV0, NV0, and then you just get 1 because these states assume they're normalized, and then you get a minus sign if there's a fermion in here, and then you would get a minus sign of E, NB, and 1. Okay, and you sum over all possible NBs. And then you can say this is the sum of energy states which are 0, okay, of basically what? If the energy state is 0, right, then yeah, then you're essentially counting how many bosonic guys you have here, right? So this is kind of the sorry. So this is kind of the what this guy is the number of bosonic states with 0 energy minus dimension of F0, which is then the number of fermionic states, meaning there is a fermion with energy 0, with 0 energy. And then what would be the rest? Well, the rest would be a sum where E is not 0. Well, we said they come in pairs. Right? So you can reshuffle actually indices if you like. But eventually what you find, because you sum over all numbers, right? Okay, let's probably write it. Plus something where the energy is non-zero, so this is bigger or equal to 0, right? And then you have this energy and beta 0, and let's say I want to treat it, this guy, I just want to treat it for the pair, right? Because I can write it as minus beta n b plus 1, 0, and this is somehow the energy of this thing, right? And there's a beta. And what happens, since I can just shift in this kind of dummy index here, actually they will cancel out. Okay. So upshot is this partition function is just given kind of by this dimension of 0 energy states which are bosonic minus dimension of 0 energy states which are fermionic, and it doesn't depend on beta at all. Yes.
Sorry, could you elaborate a bit?
Yes.
Maybe it was
No, absolutely.
lost. What do you mean with 0 energy? Like
The
E
energy
equals to
is
0?
0. You can have 0 energy, right?
But you can only have 0 energy if both numbers are 0,
In
right?
this case, yes. In
But,
this case, yes. But let's do it.
Generalize this.
Exactly. Let's just think about it formally.
Like as a
It's a
series.
complete overkill and might be just 0. That's fine.
So you
Or
basically
one.
enforce that it's like nb minus nf on, and you sum over all possibilities where this cancels out.
Yes, in this case, for this example, yes. But then basically, this case is too simple because NB must be 0 and F must be 0 to have 0 energy, so this is 1 minus 1 is 0. Or just, yeah, kind of. Actually, no, sorry, what I'm going to say is that there's just one state with 0 energy. Okay, so you don't have to actually go through this. But imagine that I just forget about where we came from and just say, oh, we have a Hamiltonian, and this Hamiltonian has these properties, right? There's a symmetry of these properties, and then just kind of try to calculate.
So you look at the generic Hamiltonian now.
Yes, like in my head. So like you can write all this down, and it's complete overkill because it's too complicated, but now you could just easily generate because you can just forget where it all comes from and show that these properties actually apply.
So basically you just have the assumption, we look at some kind of Hamiltonian which has which is degenerate for n and
Yes.
n, b and nf. That's it. But it doesn't have to be like n's can be in
Yes.
z.
Yeah. Essentially, why is that? Let's do more abstractly, saying that this is this state nb plus 1, 0, but we can act with q on it, and then if you look how q is defined, right? Then this is just nb and 1, right? So what this means is that these pairs of energy, they come, if you find one with the energy, you can just apply Q or Q star to it, and then you find your pair. So this is a complete general fact that these things come actually in pairs, and you can prove it essentially by using this relation as we did before with the commutator guys. So what I'm trying to say is now that yes, here in this case that might be 0 or 1 or something, but for general supersymmetric quantum mechanics, which is defined by these properties, you can have. And the important part about this thing is this is not there, but this was some kind of measure of something, right? Because it's temperature, we can measure temperature, it introduces kind of a scale, a scale of some sort, namely of temperature. But we find that the theory, if it has these symmetries, is just independent of the scale, which is amazing.
Sorry, one more thing. Like, you define a supersymmetric quantum mechanical theory with these three properties. Is this like a definition?
Yes, exactly. Definition would be, because we like that so much, would be that a SUSY quantum mechanics is a quantum mechanics such that there exists Q and let's say Q star, which have this properties that Q. Sorry, I don't even need them. Oh yeah, Q squares to 0, and Q star is your Hamiltonian.
The last one you don't care about?
It follows from here.
Yes, it does. Yes, it is.
Q star to square to 0 as well, or just Q?
Usually, yeah, you can, let's say Q star squares to 0 as well. Yes. Usually it squares to 0 because it's kind of dually defined to Q. Okay? So, okay, sorry, I'm over time and I should stop here, so let's stop with this definition. Sorry. All right. I just want to say a couple of things. Let's say typos, right? No, I did a couple of mistakes. So, first of all, the thing is just defined as a trace over this Hilbert space. So there was a sum before Hilbert space, which makes absolutely no sense. Please forget that. So it's just a trace of this Hilbert space. So then there were a sum over this kind of dimensions, but this is of course not true because we already carried out the sum over energy zero states. So there was no sum here. Another thing I wanted to say is that if you look at this sum and then you take out the energy zero states, you know, if you look at this, NB can still be zero right here because it has energy 1. So this sum actually runs over NB bigger or equal to 0, where you have NB plus 1. This is just bigger than 0. And then you can see that the sums cancel actually. So that's good. And one more thing is, okay, because I think I was confusing. In our case, for this harmonic oscillator we used as a motivation, right? What is actually these guys? Okay. So what is the state which has zero energy, well, it has zero occupation numbers of both bosons and fermions, meaning it's this state, and this is bosonic. Okay. So the dimension of zero energy bosonic states is 1. So what is this? Can there be any fermionic state which has zero energy? No, because again the energy would be is 0 even only if both of these occupation numbers are 0. Okay, so if there's no fermion, it's not fermionic. So this is 0. So in our case, this Z beta is just 1. Okay. But I tried to say that I did all this abstraction, kind of do the calculation completely overkill to say that, oh, okay, now I can think about examples where this would not hold true, and they can have different dimensions because they do not come in pairs, right? So as long as I have this definition that I have like a quantum mechanics, and I have an odd symmetry and Hamiltonian, I have an operator Q squaring to 0, and it's dual, let's say, and the Hamiltonian is you know, can be expressed as Q and Q star, then all of the properties we had before, they follow, and you can equally show same calculations that you have positive, like the Hamiltonian is a positive operator, that non-zero energy states come in pairs, the whole calculation goes through them abstractly. And then I do not want to say this at the moment. Yes, so upshot is taking a square root gives very nice structures. But Q squares to 0, it's an odd guy. You call it an odd symmetry. Okay? But this is a lot of structure. Okay? So actually, if you would like to make a connection to what we said this morning, Q squares to 0, right? So let's say we had fermions, right? Now let's say we have many, and then you can take your Hilbert space, and then you can say it's a grading, right? So it's a sum over states which have no fermion in it, and then probably with 1, and then so on and so too, and so forth, right? But now you have maps between them, which is this Q, right? Which turns this thing actually, so this is fermion number. So this turns this thing into a complex, a differential complex suddenly, right? Like the complex we saw this morning, like the Durand complex, for example. Very nice example is the Durand complex, where you say dx is a fermion. Now you can wedge dxi, dxj, dxk, etc., right? And then they have different fermion numbers, and then Q could be, for example, just a Durand operator. This would be an example. But now it would be interesting to compute in this case. So this, let me put this as a homework exercise kind of thing. Compute the cohomology of Q, okay? And then relate it to energy spectrum. And then you'll find some interesting observation, and we can talk throughout the week about this, okay?
Sorry, can I
Yes.
ask some questions? So I'm confused. So the superscripts H
These things here are just calling fermion numbers.
So they're different from the super
Yes, yes. It's different from here. I should probably put down 0 here to indicate it's 0 energy, and up is fermion number.
But I'm still confused by this fermion number, because isn't it supposed to be just 0 and 1? So what's H2?
In our example, now if you generalize, you can have more different types of fermions, let's say, so they
You
can
just
be
count how many of them
Exactly.
in total. Okay.
Yes. So I can have C1, C2, C3, etc.
Okay, yeah.
Okay. What allowed us to do these things and come to this nice structure was that these fermions, like the C, right, or the C star, the creation operator of these fermions, squared to 0. So it's like a nilpotent element in our algebra, right? So maybe it's actually a good idea to study these things, okay? So if you do this and you follow along with this idea of fermions and bosons and you want to distinguish them, you come to the mathematical part and foundation of this, which are superalgebras. Okay? And superalgebras is a very big word for something you should not be afraid of, because it's something called a Z2 graded algebra. And let me just put on the board what it is. So, okay, super vector spaces and superalgebra. Oh. So essentially, we just want to kind of formalize or mimic these construction and the idea that you had a bosonic part of your Hilbert space and a fermionic part. Okay? Or you have a bosonic part in your algebra and a fermionic part. So, okay, a supervector space is a Z-mod 2 vector space. Let's say over R, okay? I always assume that we work over R. Let's say V, which comes equipped with a given decomposition, or let's say here, given composition, so V, it's V1, V0 plus V1. So we would call these even or bosonic, and these guys, elements in V1, are odd or fermionic. Think of A's and C's and stuff. And then there's a parity map which is defined, so it's a map from V into Z mod 2Z, so that is kind of giving you the grading, which is defined by on homogeneous elements, so elements purely in V0 or purely in V1. So V0 is 0 if mod 2, okay, if V is in V0 and V is mod 2 1 if V is in V1. Okay? So you just have a decomposition of fermions and bosons. So since we have now this definition of vector space,
Sorry, just one question.
Yeah.
What's the element? Like, what are the elements of the vector spaces? The states?
yeah. So definition, now since we have these vector spaces and they come with this decomposition, we have a new structure, so let's see what are maps between these supervector spaces. So if we have two supervector spaces, a homomorphism, so I'm saying homomorphism because when you read homomorphism, you should think, oh, it should preserve the structure we have, right? So it is a map F from V to W such that F is linear. And what is the extra structure? It's the grading, right, with the parity. So it's grading preserving. What this means is that essentially, if you map VI, then this should be contained in WI for I being either 0 or 1. Okay, this is all good, but let's do examples because it's easier, I think, to understand in examples. The first example is R, which we will denote RPQ. And this is what? This is just RP plus RQ. Okay. So we just take two copies of R, we give this decomposition, and we just declare one of them to be odd. Right? Like Q looks in the wrong direction, it's kind of odd. So let's say this is odd, guys. So this is V1, this is like even, right? This is then V0. So what we'll do later then is just imagine, let me not do this. Okay, let's just do more examples. Yeah.
Going back to the definition of gray pairing map, so our space is the direct sum of space. So what if we want to consider the vector which is sum of the vectors from different...
Yes, but this is, yeah, exactly. Yeah, you get like a sum, right? But now I said this is defined on homogeneous elements, so guys only in here or guys only in here.
So it is not defined on the sum.
No, it's defined on, well, it is, but by linearity. I know. Yeah. Like if you would have two guys in one and you would apply it, then you would like to say that these two guys kind of become even. Okay, two times, like odd times odd is even. -1, -1, kind of 1. So what you kind of do is that you say you extend this map by linearity. So you just need to define it on homogeneous elements. Does it make sense? Sorry. So suppose you have a V0 plus a V1 or something, then what would be the parity of this guy in this case? It should be V0 plus V1.
But it's an element of what?
In Z2, right? I mean, like you mod 2. So you say this is 0 plus 1 mod 2, or you could have like a V1 prime. Then you have 1 plus 1, which is 0 mod 2.
Okay, then if I want to add two vectors from V1,
Yeah, that's what I'm saying. You have V1 plus V1. Oh no, this is just still in there. Sorry, no. It's just defined on. Oh, that is right. Yeah, no, sorry. It's just defined on homogeneous elements, not on the sum. Sorry. Yeah, we come to that later. This parity map. Sorry. Yes. So it just basically singles out what V0 and V1 is. This kind of. It'll be better in algebra. In algebra, there's kind of a sum coming. Sorry. Yes. There was another question here?
And it was amounted to the same thing.
Oh, okay. So yeah, sorry. Let me clarify just on homogeneous elements. It's supposed to give you kind of the grading. It's supposed to tell you what is what, roughly. Like the homogeneous element. Okay. So the second example is if you have W being supervector spaces, then all their homomorphisms, let me write it like this. So these are just these maps, homomorphisms from V to W. This is also a supervector space. Okay? So this is an exercise probably to prove, and it's instructive to think about it. You just have to see how can you define basically this decomposition. The home thingy?
What you just said there, it should be degree preserving.
Yeah.
So So it's like even super.
But you can take F.
We want to say is all the linear mappings.
All the what?
All the linear mappings between V and W.
If it's grading preserving, then it's just an ordinary
It is just even. I mean, it's still true what you say, but it's probably not.
Oh, okay, yeah.
And the usual, the notaries, I think the usual notation is home underlined.
Okay, all linear maps.
Yes.
Yeah. Okay. Yes. Yes. Yeah. Okay. Thank you. That's true. That's true. Yes. Not necessarily preserving the grading. Just linear maps between the vector spaces. One other important example is if you have.
So why is that a super vector space?
That's kind of the exercise, but the idea is like consider maps 0 such that, for example, V1 is 0, like hint, and maps F1 which F0 is 0, and then you can put them together into a map F0 plus F1, but you know you get like a decomposition, and then you can go on and kind of show. So if V is an ordinary vector space, then you can define pi V. Yeah. So this would mean ordinary vector space would mean that V is essentially just all in V0, right? And then pi V kind of. It would mean that V is considered to be V1. Okay? Put differently, if V is actually V0 plus V1, then pi of V is, okay, pi of V0 plus pi of V1, but this is V0 and this is V1 of the original. So it basically just changed the parity, okay? So it makes even things odd and odd things even, just considering it to be that way. I think I'm losing people, so.
So in your first example, your RQ is secretly PRQ. No, this is fine, but plus PRQ by RQ.
Yes.
Secretly.
Yes. Yes. Yes, absolutely, absolutely. Just swaps it. Yeah, perfect. Yeah. Yeah, that's probably good. Example, pi R PQ is R kind of QP. Okay. We just swap what is odd and what is even. Okay. Good. Another important one is if W is ordinary, like I used to say ordinary, but it's just, yeah, ordinary vector space to distinguish them from supervector space, then you can consider V the exterior algebra of the supervector space, right? So this decomposes into even and odd, right? So this gives you your V0 and this gives you your V1, your odd guys. And actually, if you think about it, so this has finer grading. This has actually a Z grading, right? So you can do 1, 2, 3, 4, 5 in the exterior power. So this would be kind of what's called a Z grading, okay, this decomposition. But we are mainly interested in its mod 2 reduction, meaning that we just collect every even and every odd guys. And then the only one thing I want to say is, what are functions on supervector spaces. Like, how would we like to define them? And let me just kind of give you the definition. So I will always write C infinity. Please don't comment on the analytical properties and things like that, but like it's a function, okay, in an appropriate sense. So it's overloaded symbol now. So if V is a V0 plus V1, a supervector space, then functions on this V are defined to be the functions you consider on the usual guy, just on V0, that's fine. And then tensor the exterior power of V1 dual. Okay, so we will take this as a definition. And what we should think about is that if you have a function, let's say f, and let me actually give these now coordinates, okay? Let me say these have elements x and these have elements theta. You may have many, okay? What you would like to think about is that these odd guys, what they should do is kind of, they should secretly be the same as these fermions, so you should secretly kind of square to 0, okay? So what would you do then if you think, you know, oh, if they would square to 0, what would be a good notion actually of a function which depends on these coordinates? Well, then you would say, like, okay, maybe it's good to Taylor in theta, okay? And then you can take this as a definition, and then you get like an f0 part of x, and then you get fi of x theta I plus fij of x theta I, and then theta j, and so on. And essentially what you're doing is you're generating an element in here, and you will actually stop at some point, because if you have more thetas than the dimension of your odd part of the vector space, then it's 0. This is just saying that this exterior algebra is finite dimensional. Okay? And if you wonder if, like, yeah. Okay, so functions are defined by Taylor expansion in the odd variables. Okay, and the odd variables are just elements in the odd part of the tangent space. Okay. Now, since we're talking about functions, we probably would like this to be, you know, like algebra, so we would like to have the notion of a super algebra. Let's do that. Or let's give a an example. Like, note, if W was this ordinary or n ordinary vector space, and we look at V, which is the exterior, let's say, power of, like the exterior algebra of this vector space as a supervector space, so again, even and odd. Then you can note that this exterior algebra has more structure, right? For example, it has a wedge product. So you can say alpha and beta in here somehow, and then alpha wedge beta is in here. So there's a multiplication lambda, which goes from V times V to V in this case. And it has the properties, namely, if you look at, if you have like a K vector and an L or M and N, right? Degree M and N, then the wedge has degree M plus N, right? So if you would look at this kind of parity map, you would have that the parity of alpha and beta is just alpha plus beta. If the parity in this case would be the degree of your multilinear vector, like yeah, of your element. So this basically means this multiplication is kind of compatible with it's compatible with the grading. And let me just give now the formal definition of putting this into this idea into a definition. Like in associative superalgebra, is an associative Z1 to Z graded algebra A, like A0 plus A1, equipped with a product such that AB is A plus B. Here's the end of the definition. And let me just continue. And we say that A is super commutative if you can actually swap A and B. However, what you would like now, you need to look because everything has grading and so on. So now there will be a sign. Okay. So now you will see that this is true if this has -1 and then power A, power B. And again, take the example in here, right? So if you have alpha wedge beta, then this is beta wedge alpha, but you can sign by the degree of alpha and beta. Okay, so this is just saying that the exterior algebra of an ordinary vector space can be considered as an associative superalgebra which is supercommuting. All right. Yes. Let me give examples here. So, first one is any odd, like it's a bit bad, but like if you have A an ordinary associative algebra, then A can be considered as just the even part of a supercommutative, as a super, like an associative superalgebra. Right? It doesn't have to be commutative. Then, as I said, we have a vector space, just ordinary. We have A to be the exterior power of V and the wedge product. And you can actually realize this guy as follows also. Okay, let me just put it this. 3, it's kind of the equivalent definition of this. But you could take the algebra A, which is generated in theta 1 to theta n elements, and you can mod out by a relation, and the relation is that theta I, theta j is minus theta j, theta I. Right? Like this morning we saw if we had just one of these guys and we squared out by this relation, which namely is squares to 0, right? So this was the epsilon from what we've seen this morning. And then, yes. So to be able to come back somehow to nice, interesting physics, which we can do with it, we need to talk a little bit about, so like these super vector spaces, they're kind of under control, right? They're like just vector spaces, and you just have, you know, this decomposition. But this is all the linear case, so what and how could we now translate these examples or these ideas of having this decomposition and probably having odd elements to something which we would call a manifold, okay? And the mathematically precise definition is rather involved, I would say. But I will I want to kind of give example and look at it, what it could be, and yeah, just give holistic definitions. So, let's say, towards the notion of a super manifold. So, in differential geometry, I would say, or I heard, always refer to authorities, right? So there's the slogan that you may or may not think globally, but you work locally, right? So if we follow this, then in that sense, what is an ordinary manifold? Let's say modeled on Rn. Well, it's a space which locally kind of looks like Rn. So in particular, we would say then this has coordinates xi, even. Well, let's be kind of naive. Then a supermanifold, what should it be? Well, we could try to model it not on Rn, but the next best easy super vector space, which would be Rn/m. Okay? Which were just these two copies, right? So this would have, let's give coordinates to these two copies. So let's say, again, xi is even. But then you would have also coordinates on the second copy, on the odd part, where theta I is odd. Okay. And what we mean by this kind of odd coordinates, we will see in a second, but essentially it will always amount to the property similar to this, okay, that they square to 0 and that they kind of anti-commute. If you think of them, for example, as coordinate functions, then you could kind of multiply them and exchange them. So that would be idea one. So what we would then do is we kind of would need to glue these patches here, right? And then I should tell you how to glue these patches, and this is where it will be very hand-wavy, but I give an intuitive kind of example and idea. So the second idea, so this is essentially probably differential geometric, and the second one is more algebra geometric, where the idea is that instead of the manifold and you look at it locally, you describe it by its ring of functions. Okay, again, I'm sorry I'm overloading this. The symbol is not like, like if the manifold is smooth, I want to take smooth functions, but if not, then you take the appropriate notion. So what this would basically mean is then, okay, locally, in supermanifold, should be described or should be an object whose ring of functions are as follows. So, sorry, are of the form functions on U tensor some exterior algebra of V star, where probably U is this local kind of chart we would like to take, like an open. To see that these two different, like these two ideas are actually, you know, be okay together, right? So if we take functions here in R and M, then we would, you know, like, if you look at what are functions of R and an M, then, you know, kind of by this definition what we had, right, they're just defined to be functions on this even part, right? So where we had these coordinate xi, and then we had these exterior algebra, essentially, of R, M dual, but this is essentially the same as these kind of functions here, okay? So they're like these polynomials which are generated in these odd coordinates where theta I and theta j anti-commute. Sorry. Yeah. Right, where on the second part, yeah, we had like coordinates xi and theta j. Okay. So
Before you erase, so just if my intuition is correct.
yes.
So should I think about your multiplication that you defined there
Yeah.
as like I look at V, which is actually dual to some vector space, and then I'm trying to figure out the coordinates on the left. No,
Here.
no. Yeah. So here you define some multiplication that behaves somehow nicely with respect to your parity.
Yes.
And now, if I look at coordinates there, I'm trying to see where they live.
Yes. In the dual.
Yes, so what I want to say that when you say it's locally modeled is that you actually take the dual of your space, your Rm dual and Rm dual shifted, which by chance looks like Rm,
Yeah.
and then thetas are just elements of those.
Yes.
And then I multiply them following the same rule.
Yes.
And this is what gives me my C infinity
Yes.
of Rm.
Yes. Yes. That is kind of, you would think that they are coordinate functions. There's a very subtle difference probably between coordinates and coordinate functions, which kind of like project into this coordinate, and I always get confused, but it's exactly what you're saying. Like I should think of them as being, these thetas should be elements of this dual projection, and then you just multiply as here. Okay. Okay, this is now a definition, or let's say an idea of what it should be. But I'm very pictorially. I can only think about these things if I can draw somewhat a picture. So how would we draw a picture of a Superman? Yes, yeah.
Sorry, just one step back. What does it mean that a manifold is described by the ring of functions? I'm just
Basically, you can say M is this manifold and it's this abstract object, kind of, and then you would say that you're just describe it by looking at all functions out of this object. Okay, you can look at all these functions, you can record what they do, and then you can say like, oh, there should be some kind of type of locality, right? So that you can basically patch them up. So you would say like, instead of like I want to look at this strange object kind of locally, and I look at it of these functions should somehow patch together to something which is defined on a global object, and this global object is supposed to be the manifold. So you would say, oh, if you want to have like a smooth manifold, for example, you would take patches in Rn, so it's still locally modeled in Rn, but you look at the functions of these patches, and then you look at certain properties, and then you patch them up together. And then you would find that this is nice. Unfortunately, well, we will have an example with these supermanifolds now. For these ordinary manifolds, since I'm not an algebraic geometer, unfortunately, at the moment I don't have like a good example, but they're
Do you still have
like C or something.
Do you still have these notions like in differential geometry with curvature and everything you still get from this definition?
If you because like the idea is now that you're looking at functions only, that you can do it algebraically, and now if you want to talk about curvature, you need to just find the right space on which you look at functions and stuff.
But it's de facto it's equivalent to the definition with charts of a manifold.
Yes.
If my intuition is correct, so just your idea too is something like xi is a function, theta is a function, so if I know all of them, I know everything.
You need also know functions of the xi's.
Yeah, but to start with, like in the smooth world, if you know all the coordinate functions, then you kind of, and you know how functions behave on local charts.
Yes.
So this is what you mean by the second step.
Yeah. Yeah. Okay.
No, that's fine, thank you.
So let's try to come up with a picture. So what is the fuzz all about, right? And let's actually try to see if we can use this second idea, like studying these objects by functions out of it, to get an intuition of what it should be. Okay, so this is an example, and I found it in these. So Fried has a book which is a big collection of lecture notes on supersymmetry, and you can find the example in that. So suppose, and now I try to make these curly, okay? These supermanifold things. Suppose we would know what a supermanifold is, and let's say P is the supermanifold, this ring of functions is given by actually the algebra which we saw this morning, namely R theta mod out by the ideal of theta squared. Okay, this basically just means that theta squares to 0. Good. So an object in here then would look how, well, we said it's kind of defined by, well, it's just this object, right? It's like, it's just this object. Yeah. So now if you, there's a certain kind of remark, if you have a map phi from M to N, or just in, yeah, let's do it like this, from M to N, then you can consider functions on N and you can consider functions on M, but actually you can create a map which goes backwards. Okay? Why? Because if you take a function here, now I'm running out of lattice, but let's say psi, then you would map this to psi composed with phi. And it turns out that this is, so this, yeah, this should be an algebra homomorphism. Okay? And why we consider what kind of algebra structure on these map, on this space of functions, just pointwise multiplication. Okay? Let's say for pointwise multiplication. Okay. So, good. Now, we want to study this P by mapping out of it, okay? So now consider M a usual manifold, like an ordinary manifold. Let's see if we kind of know what a map, if we can describe a map here, okay? So we take this dual picture, and it means kind of that you should get, so it induces a map from functions of P, right? It goes, from functions of, P to M, yeah, from M to functions of the supermanifold. And we know what these functions of the supermanifold are by assumptions. These are just R generated, like polynomials in one generator up to this ideal that says theta squares to 0. Okay. And so, okay, how does such a map look like? So, such a map looks like a map which sends F in here, right? So, and then we just give it some coefficients, A of F plus B of F theta. Okay. Now this remark becomes important, namely that's an algebra homomorphism for point-wise multiplication. So that's an algebra homomorphism. What should tell us? It says that Fg maps to, well, A of Fg plus B of Fg theta. But this is supposed to be the same as if I map first like F and G independently and just multiply them. Okay? So this should be A of F, B of F theta, and A of G plus B of G theta. Oh, I'm going late. Okay. Let me just finish this example. Right. So now, if you expand both sides, or the right-hand side actually, and compare, note that theta squares to 0, then is the following. You get the first condition, namely that A of F G is A of F A of G, right? But where does A land in? But so A is a map essentially from these functions to R because it lands in the even part, right? So here, right, this thing as we've seen this morning is essentially R plus R theta. So that's an R. So any of these algebra, like any of these things, any such A is an evaluation map for some point M, sending F to F of M for some M in M. So if we use this, like now pick M and set A to the evaluation map of M, then the second condition will read as B. Now it will depend on this M because we chose an M here, so let's keep this choice around, will be F this is like small exercise. This is the A of f here, B of g, there's an m, plus b m of f, and g of m. So what this means essentially is that b is a derivation, meaning you can think of E as an element in the tangent space at the point M of M, just because of this property. So what this means, somehow, the conclusion, and then I let you breathe, is that kind of these maps from the supermanifold and this ordinary manifold, right, they're kind of given by pairs by point M and then a vector in TMM. So somehow this can be thought of as a tangent space of M. So what it is, it's like a map gives you, so such map gives a point, right, and a direction. So if you kind of think about what it is, kind of this abstract blueprint of a point and some direction. It's a fuzzy point. Hence the title. So let's make a break here. Okay. Let me just talk only what I try to convey before the break. I want to say that we want to study this supermanifold P, whose functions, the ring of functions was this R, like polynomials in theta mod, this ideal that theta squares to 0. And then we said, like, okay, let's study what would be a function from the supermanifold into an ordinary manifold. And we kind of said, you know, algebraic rule that it gives you two things. It gives you a point and kind of gives you a direction, an abstract direction. So what then, like, it gives you a point actually in M and a direction in of this point, right, in the tangent space. So you should think about P as one kind of physical point which is mapped to that point. Okay, it's mapped to M or M prime or something. And this, whatever is attached to it, right, because you have this fuzzy thing, is mapped into a direction in this tangent space at that point. So this is kind of an abstract blueprint of the tangent space. So now, what about maps into P, right? So we're trying to understand P by studying maps out of it, but maybe it's actually nice to try to study it by probing if we send stuff into it, right? Like physicists shoot stuff at these things all the time and, you know, say like, ah, yeah, it scatters and I know what it is. So let's try to do that as well. So we want to consider maps from M, again, the ordinary manifold, into P, which gives us a map from the ring of functions of P, which was, again, are the polynomials generated in theta mod out the ideal, so theta squares to 0, which was R plus R theta into functions of M. Now, the problem with these things is that kind of these things is just purely even. There's no fuzz at all. Okay? It's just even. So the question is, like, where will we send theta? Okay? So it can only send to 0 because this still is an algebra homomorphism and theta, you know, squares to 0. So whatever we find kind of squared to 0. So it should be kind of the constant 0 map. Right? So, since C of M has no odd part, necessarily we would send theta to like the constant zero map. Like just zero. And this is since theta squares to zero, and you want plus algebra homomorphism. So, somewhat, you just send, like, you kind of kill everything. Okay, if you do that. Like, the idea is that we said, yeah, you know, you have this physical point in P and you have this direction, but these directions, they're just all collapsed, and then essentially what you do if you have to think a bit about it, but essentially M, you know, we would like to have our manifold, and here's this abstract P, the fuzzy point, right? So like, how can we map it? Well, we cannot map it into a fuzzy thing, because dually this would mean that, you know, the fuzzy thing would be mapped to a non-zero function, but it just kills all of it. So it just maps all of it to a point. This is the abstract point in P. So all of M is mapped to the physical point, let's say, in P. What this should tell us is you cannot probe fuzzy areas with no fuzz. Okay, you can only fight fire with fire. You can only probe fuzz with fuzz. So you can only probe fuzz with fuzz. So what this means is that what we should do is make M super. So what you would then do is, like, you actually would, to probe the supermanifold P, you would consider maps where you have M times the super thing, like any other supermanifold, into P, because now this fuzz can probe this fuzz. Okay, so you should say that this is kind of roughly by definition. So all these definitions I'm saying now are heuristic. That's why I'm not writing it down. But like, think of such a map as a parametrized map. So in particular, you could consider M to be just a point, and then an S-parameterized point in P is called an S point and can be used to kind of probe P. But now you have a lot of material to probe it, right? Because if you can take any supermanifold, maybe you want to take R01, but you just need to add some fuzz, okay? That's the message, yeah.
So you're saying that all functions that go from M to P have to map all M to the same point in P?
Yes.
In the previous,
Yes, and there's just one point, one abstract kind of point, one even part. Right? This is a picture which you have in mind. If you would like to make it mathematically rigorous, you need to work on the level of functions of algebra. Yes.
Maybe I misunderstand here, but it seems that there is a difference between these two examples from my mapping from the curl P and to the curl P.
Yeah.
No, I mean, what I mean is that in mapping to curly P, you seem to be only considering maps that preserve that are like degree preserving. Because you said that nothing can map, like theta has to map to 0.
Yes, that's because algebra homomorphism, right? And then in infinity of m, these functions, you know, like the only 0 divisor, like the thing which squares to 0, for every point, right? This should be 0.
I see.
Let's take m to be super nice, compact, orientable, connected. Yes.
Once again, what is S?
S is any supermanifold. Think of R01. Yeah. So you would call, if M is a point, you would call it an S point in P. It's an abstract notion. You have more information because you have to probe the fuzz. Okay, let me take the last 20 minutes to actually try to come to this thing in an example. So this would be the example 2. And this would be trying to understand what the shifted tangent space of X is supposed to be. Okay? Where X is some smooth, nice, meaning compact, orientable, connected manifold. So, okay. Let's have the first look at it. So locally, if you just take the usual tangent space, this would be essentially a point and a vector, right? Yeah, let's put in Rn. So X is, let's say, n-dimensional. But now, if you would change your coordinate, so what it kind of does, right? So you can kind of glue these vector spaces together to define a manifold. And how would you do this is if X tilde is a map of X, right? And the corresponding V tilde, it should transform as a vector. So I hope it just transforms with kind of the Jacobian. So let me give you indices here. Okay. So okay. So then how should we think locally about the shifted tangent space? Well, by definition, these will be X and psi's. Now, psi should be in PRN. So this should be kind of, what we're going to do is we take same points, but we kind of declare these vectors, to be odd. So this pi kind of just, acts on the fiber, we would say, but basically on these vectors. But then we want to glue, like, these change of coordinates. We would basically define psi to transform in the exact same manner. And then this is enough to be able to glue these things nicely together. So we can take this as our definition in terms of these local charts. Let's see if we can, again, like there was this differential geometric picture and then the algebraic geometric picture where you would like to study functions on this, right? So let's again say locally a function alpha of pi tx and x, right, to, oh my god, to r is, oh, I should not say. Sorry. a function on phi tx. Is something which is defined on these coordinates x of psi, where psi now is odd. Okay. So this is defined in terms of its Taylor expansion. So this will be some I1 to In depending on x, and then psi I1 to psi In here, and then you sum all of these guys. And now let's cheat a bit and just imagine that we already know kind of that these odd things, they transform like tangent vectors, right? Because that's basically what we mean and how we want to define it. So what if we change our coordinate again to some x tilde of x, then alpha of x tilde and psi tilde looks like the sum of alpha I and x tilde x. And then you have psi tilde I1 psi In. And then this would be the sum of x tilde of x. And now here we get the Jacobian of the coordinate transformation. So x tilde over x, we have I1 and J1, dx tilde In and dx Jn. And then we would have some psi's J1 to psi Jn. But if you look at kind of this part here, this part roughly, then you would say that alpha transforms like a differential form. Because this is precisely how these differential forms kind of change under coordinate transformations. And so yeah, basically what this means is that these functions on pi t xx is locally a differential form. But actually they glue together globally by this property. And what would be, what would be the map? Well, the map is kind of this psi I to dxi. So that's cool. So we have this algebra on this pi tx, but we have even more. So we kind of realize them as differential forms on x. But we've seen this morning that this space has more structure, namely it has this de Rham differential, right? So here we have the de Rham differential. How does it look like? It looks locally like basically you take a derivative of your coefficient function and then you wedge with dx. So let's look how it would look on the side here. So this, by the way, is a derivation, right, of this guy, meaning it satisfies Leibniz rules. So this would mean here on this side, we just replace dxi by psi I. Oh, cool. This looks rather easy, right? This is kind of, if you think about it, it's a derivation of these functions, meaning it's a vector field. Okay, so this now is a vector field on pi tx. So the de Rham operator can be thought of as a vector field. I have 10 more minutes, that's good. Let me just see how it can be even more confusing. Okay. Okay, let me give you this third look kind of on pi tx. So we can think of pi tx heuristically as the space of odd curves. So I should say with words to that. So what we would like to consider are maps which would go from R01 into X curve surface. Right? But so what we said before from this fuzzy point example, this is odd and this is something even, so we cannot map into it. So what you should basically do is you put some other supermanifold Y here, which may have an even thing, and then you can map into here. Also, you can have odd and odd things from both guys, and then map into something even here. Okay, so we look at Y parameterized, where Y is some supermanifold. Okay. So let's say we have odd coordinates theta here. Okay, let's theta be a odd coordinate on R01, and then Y be a general coordinate odd and even together on Y, then such a map locally, such a map looks like an xi of theta and y, which is some even part plus some kind of odd part, and then you have another odd part. And this other odd part here comes because, you're now mapping out of y as well and can have odd parts. So you have even and both of them are odd. So then, again, do a coordinate transformation. So then let's say xi tilde of a coordinate, but this coordinate now is a map of theta and y. So this is xi tilde of x of y plus theta psi of y. So by tailoring, by definition, this is x tilde I just here, and then you would have some theta, and then you would have the derivative of I x j psi j. And then essentially what this means is that you can take this as be your psi tilde I, and then more or less almost by definition this psi tilde I or these psi's, they're again kind of transforming like vectors. So again, psi transforms like a vector. Excuse me. So what this means is kind of that these maps from R01 times y into x, where you have xi of y plus theta psi of I, they can be actually seen as maps from y into pi tx, where now here you have the point and the vector. Excuse me. Okay, so the very last thing I'm going to say is that it's very nice to have these, yet another point of view on pi tx, right? Meaning it's a very good example, kind of, to get intuition. So all of this is, as I said, heuristic definitions, and it's supposed to be into, like, give you some intuition so you can go out in the world and then learn these things rigorously, okay? So, what is good about this space? Right? This space is nice because if you consider R01, then you can consider actually automorphisms of this space. And then I'll say in a second what it is, but I just want to say that these automorphisms then act on, you know, these functions, or these maps. We call them maps. Right? So, what are these automorphisms? Well, they should be considered as maps, and then, no, actually you can just go from R01 to R01. And they should be invertible. And so, how do they look like? Well, you would like to map the odd coordinate theta to some new coordinate theta dash. Okay, let me actually consider parametrized maps, because I just always considered parametrized maps. And then, so these should be some A of S theta plus some beta of S, where A of S is in R star. This is important to be invertible. And then beta of S is kind of odd. It's an R 0, 1. And so, okay, this is nice. So let's look at this action. So then, if you take an automorphism and act kind of on this map, then how should it look like? Well, these kind of maps, right, we said locally there's some x and there's some theta. So it just maps on theta. Okay, it just acts on theta. So then the action of this automorphism group on the space of R01 times y into x is given by an element like x dash plus theta dash psi dash. They all look different, and then essentially you have here just x, so you leave it alone, but then you act with the theta, right? So you have a theta plus beta and psi, right? So now what is this? This is x plus beta psi plus a theta. Okay, so since this is odd and this is odd, this is even. So all of this is even, and okay, you still have this odd. So meaning, so is generated by the vector field, by vector fields d, which is psi I d dxi, right? Because if you think of this as a vector field on your space and you flow kind of beta long, whatever that may mean, you would generate this term, and you would replace x by beta psi. And then you just have, sorry, I'm missing some psi here. And then the other guy, right? Then the other guy would be another second vector field, which would just scale psi. Right? So y, so I should have done this like psi, and then you would have theta here. And then you just compare coefficients of this theta, right? So the psi dash is a psi, and then the x dash is the whole thing. So, okay, meaning we already seen this is de Rham differential, meaning the exterior derivative. And then this heuristically looks like dxi del del dxi, which kind of would be just the degree map on differential forms, right? So it would map alpha k to alpha k, and it would map alpha to k times alpha. It just gives you the degree. Yeah, so since this comes to an end, let me probably come to, and then also, so the first remark is that, so what I want to say is like, okay, the first remark is the Rham differential and the degree, so and grading on differential forms on X comes kind of from an out R01 action on these maps from R01 times Y to X, which we want to think of pi tx. So this is actually a general result. So somehow if you have a representation of this guy, it is equivalent to a grading and something which squares to 0. Actually, to see that this squares to 0 is very neatly, right? Then there's just no x dependence. So, you know, b squared is something like 1/2 dd, and this is 0, and here the bracket is not 0 on the nose, because this is an odd element. If you swap the psi's, you get a minus sign, which turns this minus sign in between to a plus sign, which is just d squared. Yeah, the last kind of other remark, because we've seen it in the Cartan magic formula. So if you think about what, there exists another nice vector field on pi tx, right? So if v is just a vector field of x, then you can say iv, which looks like vi of x d psi I. Okay, this is a vector field here. And what will happen is that this is the contraction. It is literally the contraction with v, you know, acting on differential forms. Why? Because this heuristically it looks like vi dd dxi. So you take out a dx and you replace it with the coefficients of the vector field, which does exactly what the contraction does. And then, you know, the Lie derivative or Cartan's magic formula kind of comes from dib, and you can show that this gives you an expression of LV as a vector field in here. And then you can actually count degrees. So this takes out something which has degree 1. So this guy has degree -1, while D takes something out, or, you know, takes a derivative that's degree 0, but adds a degree, so this has degree +1. So if you consider this guy, it has degree -1, +1, has degree 0, so the Lie derivative has also degree 0. This is nice, so it checks out. And yeah, this is all I want to say. Thank you.